Okay, everyone, so part two now. We're going to start going over the algebra of complex numbers. And so by that I mean go over what commutative laws, associative laws, and distributive laws, and stuff like that. Trust me, at first it seems trivial, but this stuff over time will become more and more non-trivial as we get deeper in. All right, so commutative law. So this will be our law one, commutative. Commutative law says if we have z1 plus z2, this is the exact same as z2 plus z1. So the order in which we add doesn't matter. So it's commutative addition. And lucky for us, multiplication is also commutative. So this just means that z1 times z2 can be written as z2 times z1. All right. So we got commutative out the way, which I just realized I totally spelled wrong, but I mean, you get the idea. So next is the associative law. Oops. Now the associative law is for addition. It says that z1 plus z2 parentheses plus z3 is equal to z1 plus parentheses z2 plus z3 in parentheses. So it's saying no matter how you add them up, it's all going to equal the same thing. So if we had three things adding each other, we don't have to have parentheses stating what we're adding first or adding second, because the order of the addition does not matter. Now this is the same for multiplication. So multiplication, we can have z1 times z2 parentheses times z3 is equal to z1 open parentheses z2 times z3. And these properties can be proven from just our basic definitions, which is some of the I looked over some of the problem sets at the end of this chapter, and those are some problems. And we could possibly do those in a future video. But for right now, I just want to go over the basics. Okay, next thing we have to go over, number 3, distributive law or property. Okay, the distributive property is exactly what you remember from regular algebra. Z1 times the parentheses of Z2 plus Z3. We have to distribute Z1 to each of the terms inside. And we get this being equal to Z1 times Z2 plus Z1 times Z3. And from the commutative laws, I could also write this as Z2 times Z1 plus Z3 times Z1. So that's by using the multiplication of commutative laws, because I just switched the order of multiplication. But remember, addition is also commutative, so I can switch to this order too, because this could be Z1 times Z3 plus Z2 times Z1. All three of these are the same thing. And we could probably do it another way, but that really isn't productive. So let's continue on. Now, the fourth thing is that there is an additive identity. So the additive identity means that, so if we have a complex number z and we add it to the identity, which I'll just call, why did I do it like that? Let me just call it I, a capital I for right now, is equal to itself. And so for regular numbers, if we don't want to change the value of it, we just add 0 to it. And in this case, that's also true. So z plus 0, 0 is equal to z. This right here is the additive identity, because this doesn't change the value of x or y. You see? So it doesn't change the values of anything. And there is also a multiplicative identity, which shouldn't be that hard to guess what that is. So identity. So z times the multiplicative identity is equal to z. Well, we can think back to real numbers. Any number times 1 equals itself. So let's try 1 to see if that works. So x comma y times 1 comma 0. So notice that the imaginary part of this complex number, or our multiplicative identity, is 0. So we're going to apply the rules now. So it's x1, which is just x, times x2, which is just 1, plus y1 times y2, which is 0. This right here is the x3 component, so all of this. There's the x new, so x, I just call it x3. And now we can do the y component. So the y is equal to x1, which is x, times y2, which is 0, plus y1, which is y, times, y1 times x2, which is just 1. So this is going to equal to, so we can obviously see this term goes away, and this term goes away. And we're going to be left with x comma y. So we indeed see that our multiplicative identity is equal to just the real number 1 again. Okay? Useful things to know. So now we get into... Alright, so actually before we get into the really interesting stuff, there's another thing that from basic algebra we probably all know, but it's good to go over. Associated with every complex number, so z equals x comma y, there is an additive inverse. So additive inverse. That means that z plus its additive inverse is equal to 0, or the additive identity. And to figure out what this is, we just solve some equations. So here, right here, this is x comma y plus, in a, we'll just say this is xa comma ya. This all has to equal 0, comma 0. And so this would be x plus x, x plus xa has to equal 0, and then y plus ya has to equal 0. Now these are basic algebra equations to solve. We'll just subtract x from both sides, and on this one we'll minus y from both sides, and we see that xa is going to equal to minus x, and ya is going to equal to minus y. And so we can say that our additive inverse for any complex number is going to equal to minus whatever the x value of our complex number is minus the y value of our complex number, which is equal to, we can pull our negative out front and we get minus x comma y, which is just the negative of whatever our initial complex number is. And this makes sense because with regular numbers, say if we had 7, the additive identity, the number that's going to, or the additive inverse, the number that's going to make 7 disappear and go to 0 is going to be minus 7. Okay, and so additive identity is right here, just minus the complex number. Okay, and let's see here. Now multiplication, we expect there to be an equivalent such thing, a multiplicative inverse. A multiplicative inverse, well, you know, with multiplication, the inverse is usually just divide the number. So there's going to be an exception to this one. For this one, there can be a multiplicative inverse if z is not equal to 0, 0. But for all other z's, it should be possible. Okay, so now let's figure out what this identity is. So we're going to do the same thing as last time. We're going to say let z equal to x, y, and our multiplicative inverse equal to x m y m. And we're going to multiply these two together. Z times m is going to equal to x times xm plus, excuse me, it's actually a minus. Is it a minus? Yeah, it's a minus. Minus y times ym, comma, then we're going to have xm times ym, not ym, excuse me, times y plus ym times x. And so the multiplicative inverse, I should have told you what this means, is equal to the multiplicative identity, which is 1, right? And so now we have to make this part of the equation equal to 1 and this part equal to 0. And we can do that right here. So x times xm minus y times ym has to equal to 1, and then xm times y plus ym times x equals 0. So I think the simplest way to solve this equation, or the system of equations, is to start with this bottom equation, solve for either xm or ym, and then plug it into this top equation. So I'm going to use the bottom equation and solve for xm. So xm is going to equal to minus x divided by y times ym. Now I'm going to use this equation and plug it into my very top equation. And I'm going to get x times negative x divided by y times ym minus y times ym is equal to 1. So there's going to be a negative in both terms because this negative is going to come out front. So I'm going to multiply both sides by a negative. When I do that, this negative cancels, and there becomes a negative in front of my 1. Now I'll be left with x squared divided by y times ym plus y times ym is equal to minus 1. And right here, I am going to factor a ym out of this left-hand side and divide by whatever is left over. And I see that ym is going to equal to minus 1 divided by x squared divided by y plus y. And now when I want to simplify this right here, I'm going to multiply this y by y over y. And the simplified version of this you can check is equal to minus y divided by x squared plus y squared. Awesome. So we're going to mark this down really quick. Ym is equal to minus y divided by x squared plus y squared. Now we can use this ym to solve for xm. Xm is going to equal to minus x divided by y times ym, which is negative y divided by x squared plus y squared. And here we can see that this negative y and this negative y are going to cancel, and we're going to get that xm is equal to x divided by x squared plus y squared. So our multiplicative inverse for any number is going to equal to x divided by x squared plus y squared, comma, minus y divided by x squared plus y squared. And so obviously they have a common factor that can be brought outside. So this looks a little bit simpler. So it'll be multiplicative inverse equal to x squared plus y squared times x, comma, minus y. All right. And so let's see if there's any more to this section. I think this right here is going to be a great place to stop. So main takeaways I think are useful are the inverse identities. So I'll write them out one more time. Z plus our additive inverse that equals to 0 is any a that is equal to minus z. And for our multiplicative inverse that satisfies z times m is equal to 1, 0 is when m is equal to 1 divided by x squared plus y squared times x, comma, minus y. Alright, so this should be the main takeaway from this video. I hope this helped you out in any way. And if you like these videos, please consider subscribing, liking the video, sharing it, all that good stuff. I appreciate you, and we'll see you next time.